Tonight the journey begins toward the nearest great galaxy beyond our own. The Andromeda Galaxy appears close in the night sky, yet the reality of reaching it is almost impossible to comprehend. Across unimaginable distances through the vast emptiness between galaxies, even the fastest spacecraft humanity has ever built would need far longer than human civilization has existed. As this story unfolds, discover what the journey would truly look like, how long it would really take, and why the answer is far more astonishing than most people realize. If these cosmic journeys help with relaxation, learning, or sleep, please take a moment to like the video, subscribe to the channel, and settle in for tonight's voyage across intergalactic space. Earth remains the starting point for all known human-made journeys towards space, and its environment defines the first and strongest barrier to any movement outward. The planet holds a dense atmosphere bound by gravity, a layered shell of gases that becomes thinner with altitude yet remains significant far above the surface. Near sea level air is thick enough to support breathing and weather systems, but it also creates strong resistance against motion. Any object attempting to leave Earth must first pass through this dense layer where friction converts motion into heat, and where structural stress builds rapidly as velocity increases. At the lowest levels of ascent, rockets operate within the troposphere, the region where weather systems form, and where temperature and pressure vary continuously. The air here is turbulent, and motion through it requires careful shaping of vehicles to reduce drag. As altitude increases, the atmosphere transitions into the stratosphere, where air becomes thinner and more stable. Even here, however, molecules remain numerous enough to interact with fast-moving craft, and energy loss through friction continues to matter. Beyond these layers lies the mesosphere, where air density drops further, and temperatures fall significantly. This region begins to resemble the conditions of near space, yet it still contains enough particles to influence high-speed travel. The thermosphere follows a region where solar radiation begins to ionize particles, creating charged layers that interact with magnetic fields. Here, the concept of a solid atmospheric boundary disappears, replaced by gradual thinning rather than a clear edge. Above the thermosphere lies the exosphere, where individual atoms and molecules are so widely separated that they can travel long distances without colliding. This region represents the transition between Earth's atmosphere and outer space. Even here, the gravitational pull of Earth remains strong enough to hold some particles in slow, extended orbits. The idea of leaving Earth is therefore not a single step, but a continuous process of moving through diminishing layers of influence. Escape from Earth requires reaching a velocity known as escape velocity, the speed at which an object can break free from the planet's gravitational field without further propulsion. For Earth, this speed is about 11 kilometers per second. Achieving this requires an immense expenditure of energy, because gravity constantly pulls objects downward, while atmospheric drag resists upward motion. Rockets achieve this by expelling mass at high speed, using the principle of conservation of momentum to push themselves upward in stages. The launch process begins at the surface, where engines must overcome both gravitational force and atmospheric resistance simultaneously. The lower stages of a rocket are designed to operate within the thickest part of the atmosphere, where efficiency is reduced but thrust must be maximized. As the rocket rises and air becomes thinner, later stages operate more efficiently, eventually allowing sustained acceleration into space. During ascent, the experience of leaving Earth is not uniform. Acceleration increases gradually and the sensation of weight shifts, as gravitational influence weakens slightly with altitude. However, Earth's gravity remains strong even at hundreds of kilometers above the surface, and objects in low Earth orbit still experience most of the planet's gravitational pull. Orbit is not a state of zero gravity, but a continuous free fall around Earth, where forward motion balances downward acceleration. Once orbital velocity is reached, the perspective of Earth changes significantly. The planet's curvature becomes visible, and the atmosphere appears as a thin blue layer surrounding a solid sphere. Weather systems can be seen spreading across continents, and the separation between surface and space becomes visually clear. Yet even at this distance, Earth continues to dominate local gravitational conditions. The region near Earth also contains human-made objects such as satellites, space stations, and debris. These form a complex environment of motion, where objects follow predictable orbital paths, but can still interact through collisions or gravitational perturbations. This region is carefully monitored because even small changes in velocity can alter long-term trajectories. Energy requirements to leave Earth define the first major limitation in any journey outward. Chemical propulsion, which relies on stored energy and fuel, provides the necessary thrust, but imposes strict constraints on mass and efficiency. Most of a rocket's mass at launch is fuel, and only a small fraction becomes payload. This imbalance shapes all early space travel and limits the scale of what can be carried beyond Earth. The Earth departure environment therefore represents a layered system of resistance, gravity, and transition. Each stage of ascent passes through progressively thinner air and weaker atmospheric interaction, yet gravity remains a constant force that must be continuously overcome. This region is not only a physical barrier but also a defining threshold for all interplanetary and interstellar travel, marking the first separation between planetary surface and the wider structure of space. After leaving Earth's immediate atmospheric influence, motion shifts into a region still firmly held by the Sun's gravity, where the concept of space travel becomes less about escaping a planet and more about remaining in stable motion within a vast gravitational system. The inner solar system is defined by strong solar radiation, dense streams of charged particles, and a complex balance between orbital velocity and gravitational pull. Even at distances far beyond Earth, the Sun continues to dominate the structure of motion, shaping the paths of all major bodies. In this region, spacecraft move through space that is not empty but filled with solar wind, a continuous flow of charged particles emitted from the Sun's outer layers. These particles spread outward in all directions, forming a vast bubble of influence that extends far beyond the orbit of the outer planets. Within this flow, magnetic fields stretch and twist, creating subtle variations in particle density and energy. Although the environment appears empty, it contains a dynamic system that interacts with any object traveling through it. The inner solar system includes the orbits of Mercury, Venus, Earth, and Mars, each following a distinct path defined by the Sun's gravitational field. These planets occupy a relatively small region compared to the full scale of the solar system, yet the distances between them remain enormous by human standards. Light from the Sun takes only minutes to reach this region, but spacecraft require months or years to travel between planetary orbits, depending on their trajectories and energy constraints. Travel through this region is shaped by orbital mechanics, where motion is governed not by straight lines, but by continuous curves around the Sun. Objects in orbit are constantly falling toward the Sun, while simultaneously moving forward fast enough to miss it. This balance creates stable paths that can last for millions or even billions of years. Spacecraft entering this environment must adjust their velocity precisely to match or alter these natural orbits. Solar radiation in the inner solar system is intense enough to affect both temperature and materials. Without the protective filtering effect of a dense atmosphere, surfaces exposed to direct sunlight can heat rapidly, while shaded areas remain extremely cold. This contrast creates thermal stress that must be managed through design and orientation. Over time, radiation also affects electronic systems, slowly degrading components through accumulated energy exposure. As distance from the Sun increases, the intensity of light and heat decreases, but the influence of gravity remains significant. Even at the orbit of Mars, the Sun's pull continues to dominate motion. The transition between planetary zones is not marked by sharp boundaries, but by gradual changes in orbital period energy requirements and environmental conditions. Each planet represents a different level of gravitational balance within the same overall system. Between Mars and Jupiter lies a broad region containing the asteroid belt, a zone populated by rocky bodies, ranging from dust-sized particles to dwarf planet-sized objects. This region is often perceived as crowded, yet the actual density of material is extremely low. Objects are separated by vast distances and collisions are rare events. The belt represents remnants of early solar system formation, where material never fully coalesced into a planet due to gravitational disruption from Jupiter. Movement through this region requires careful navigation to avoid gravitational perturbations from larger bodies. While individual asteroids exert minimal influence, their collective distribution contributes to a complex gravitational environment. Spacecraft passing through this zone experience minor deviations in trajectory, though these are typically predictable and manageable. As the journey continues outward, the Sun appears progressively smaller, yet it remains the central reference point for all motion. The brightness of sunlight decreases steadily, and the surrounding space becomes darker, not because light disappears, but because its intensity spreads across increasing distance. Even at this scale, the solar system retains a structured form, with all objects still bound to the Sun's gravitational field. The concept of distance becomes increasingly abstract in this region. Unlike terrestrial travel, where movement is measured in familiar units and durations, space travel across the inner solar system requires consideration of orbital alignment, transfer windows, and energy-efficient trajectories. These factors determine not only how far but also when travel can occur, as planetary positions continuously shift in their orbits. Communication delay also becomes noticeable. Signals traveling at the speed of light require minutes to cross the inner solar system, meaning that real-time control becomes impossible. Instead, spacecraft must operate with increasing levels of autonomy, responding to pre-programmed instructions or local conditions without immediate external input. This region marks a transition in perception. Earth becomes a distant point of light indistinguishable from other stars except for its known position. The sense of proximity to a home planet fades as spatial scale expands. Yet despite this change, the spacecraft remains firmly within the Sun's influence, still part of a single gravitational system that extends far beyond visible planets. The inner solar system therefore represents a phase of structured motion within a stable but vast environment. It is neither close to the beginning of interstellar space nor near its end, but a mid-region, where gravity, radiation, and orbital mechanics define all movement. Every journey outward must pass through this zone where distances begin to stretch beyond intuitive understanding, and where the scale of the Sun's influence becomes fully apparent. Beyond the inner planetary region, space expands into a far colder and more distant environment, where the Sun's influence continues, but weakens steadily with distance. The outer solar system begins around the orbit of Jupiter, a region where radiation levels drop compared to the inner planets, but gravitational dynamics become more complex due to the presence of massive gas giants. Jupiter dominates this region with its immense mass shaping the orbits of nearby objects and influencing the structure of space around it through strong gravitational interactions. Jupiter itself is a vast sphere of hydrogen and helium with no solid surface in the traditional sense. Its atmosphere is layered, turbulent, and deeply active with storms that persist for centuries. The most famous of these is a massive storm system, that spans a distance larger than Earth, rotating within the planet's upper atmosphere. Although distant from Earth, Jupiter exerts a powerful gravitational pull that extends far into surrounding space, affecting asteroid trajectories and shaping the distribution of smaller bodies. Travelling through this region involves passing not only Jupiter, but also its extensive system of moons, many of which are large enough to resemble planets in their own right. Some of these moons contain subsurface oceans beneath icy crusts, maintained by tidal heating caused by gravitational interaction with Jupiter. This interaction generates internal energy, demonstrating how gravitational forces can produce geological activity even at great distances from the Sun. As distance increases beyond Jupiter, the intensity of sunlight continues to diminish. Light still travels freely through space, but its energy spreads over a larger area, reducing its warming effect. Objects in this region experience extreme cold, when not directly exposed to sunlight, with temperatures dropping far below those found in Earth's polar regions. Despite this, the Sun remains the dominant gravitational anchor for all motion. Saturn appears next in this outward journey, a planet defined by its extensive ring system, composed of ice particles, rocky fragments, and dust. These rings are remarkably thin compared to their width, forming a delicate structure that extends across vast distances while remaining only a few tens of meters thick in many regions. The visual effect of Saturn's rings is one of the most distinctive features in the solar system, representing a balance between gravitational forces and orbital motion. Saturn's moons add further complexity to this region. Some of them are large and geologically active, while others are small captured bodies that follow irregular orbits. Titan, one of Saturn's largest moons, possesses a dense atmosphere and surface liquids composed of hydrocarbons, creating a landscape unlike any other known environment in the solar system. These diverse worlds demonstrate the range of conditions that can exist even within a single planetary system. Beyond Saturn lies Uranus, a planet that rotates in an unusual orientation compared to most others in the solar system. Its axis of rotation is tilted dramatically, causing extreme seasonal variations over long periods of time. Uranus is composed primarily of ice and gas, with a cold atmosphere that contains traces of methane, giving it a faint blue-green appearance. Despite its distance from the Sun, Uranus remains gravitationally bound in a stable orbit, following a slow path that takes decades to complete. Neptune follows as the most distant major planet in the solar system. It is a dynamic world with strong winds and storm systems that move across its atmosphere at extremely high speeds. Even at such great distance from the Sun, internal heat contributes to atmospheric motion, creating weather patterns that remain active despite limited solar input. Neptune's orbit marks one of the outer boundaries of the classical planetary system, though it is not the true edge of solar influence. Between and beyond these planets, the outer solar system contains vast regions of sparse material. Small icy bodies, remnants from the formation of the solar system, occupy distant orbits that stretch far beyond Neptune. These objects are distributed across a wide volume of space, forming extended populations that move slowly around the Sun. Their motion is influenced by both solar gravity and occasional perturbations from passing stars or galactic tides. Distances in the outer solar system are so large that traditional scales used near Earth become less intuitive. The time required for light to travel from the Sun to Neptune is measured in hours rather than minutes, and spacecraft traveling through this region require years or even decades to cross from one planetary orbit to another. Communication delays increase accordingly, making real-time interaction with distant probes impossible. Energy requirements for travel also grow more complex. The farther an object moves from the Sun, the less solar energy is available for power generation. Spacecraft operating in this region often rely on alternative energy sources, such as radioactive decay systems, to maintain functionality over long durations. These systems provide steady but limited power, reinforcing the slow and deliberate nature of exploration in the outer solar system. The outer solar system also marks a shift in perception of scale. Planets appear increasingly isolated, separated by vast expanses of darkness, where no large bodies are visible. The Sun, while still dominant in gravity, becomes a distant and dim source of light. From this perspective, the solar system no longer feels like a compact structure, but rather a wide, diffuse region of space with scattered points of mass. Despite its apparent emptiness, this region contains a record of the solar system's formation. Icy bodies preserve ancient material that has changed little over billions of years, offering insight into the early conditions that shaped planetary development. These remnants act as physical records of a time when the solar system was still forming from a rotating cloud of gas and dust. Motion through the outer solar system is governed by long orbital periods and slow changes in position. Objects move steadily, but gradually tracing paths that can take centuries to complete. Stability is common, but small perturbations can accumulate over time, altering trajectories in subtle ways. This slow, dynamical evolution reflects the extended timescales that dominate this region. Even at this distance, the Sun's gravitational field remains the central organizing force. Every planet, moon, and small object continues to orbit within its influence, bound to a system that extends far beyond the visible planets. The outer solar system therefore represents a vast expansion of the same fundamental structure seen closer to Earth, but stretched across distances that challenge direct comprehension. At the far reaches of the planetary system, the influence of the Sun begins to merge with the wider environment of interstellar space. This transition is not a sharp edge, but a gradual weakening of solar dominance, where the outward flow of charged particles from the Sun slowly spreads and eventually balances against the thin material that exists between stars. This region is known as the heliosphere boundary zone, a vast and shifting interface shaped by both solar output and galactic conditions. The heliosphere itself is a bubble-like region carved out by the solar wind, a continuous stream of charged particles that flows outward from the Sun in all directions. For billions of kilometers, this wind maintains a protective cavity around the solar system, pushing back against incoming interstellar material. Within this cavity, the Sun remains the central influence, and its magnetic field extends far into space-shaping particle motion and radiation patterns. As distance increases, the solar wind slows. It expands outward and becomes less dense, losing energy as it interacts with itself and with external pressure from the interstellar medium. Eventually, this slowing creates a region where the solar wind becomes turbulent and compressed. This region is known as the termination shock, where the outward flow transitions from supersonic to subsonic speeds relative to surrounding space plasma. In this zone, particles are suddenly slowed and redirected, creating a complex and dynamic boundary. Beyond the termination shock lies the heliosheath, a thick and turbulent layer, where solar wind particles are highly mixed and energized by interactions with interstellar material. This region is not calm or empty, but filled with chaotic plasma flows, magnetic disturbances, and charged particle collisions. The heliosheath extends across vast distances, forming a buffer zone between the inner solar system and true interstellar space. Within this region, the Sun's magnetic field becomes distorted and stretched by external pressure. Instead of a simple spherical shape, it is pulled into elongated structures that trail behind the solar system as it moves through the galaxy. These magnetic fields still influence particle motion, but their structure becomes increasingly irregular and difficult to define with precision. Eventually, spacecraft traveling outward reach the heliopause, the boundary, where the outward pressure of the solar wind is balanced by the inward pressure of interstellar space. At this point, solar influence weakens significantly, and the environment transitions into one dominated by galactic conditions. The heliopause is not a fixed surface, but a shifting and uneven boundary that responds to changes in solar activity and interstellar density. Crossing this boundary represents a fundamental change in environment. Inside the heliosphere, particles are primarily shaped by solar forces, while outside they are influenced by the broader galactic medium. This transition marks the first true step into interstellar space, even though the Sun's gravitational influence continues far beyond this region. Measurements taken by distant spacecraft indicate that this boundary is not smooth. It contains ripples and folds caused by variations in solar wind pressure and interstellar magnetic fields. These structures shift over time, meaning that the exact position of the heliopause changes depending on solar cycles and external conditions. It is therefore more accurate to describe it as a dynamic region rather than a fixed border. Beyond the heliopause lies the local interstellar medium, a sparse mixture of hydrogen, atoms, helium, and traces of heavier elements. This material is extremely diffuse compared to planetary atmospheres, or even the outer solar system environment. Particles in this region are so widely spaced that collisions between them are rare, and the concept of temperature becomes defined through particle energy rather than direct contact. The transition into this medium is marked by a noticeable change in particle composition. Solar particles give way to galactic particles, many of which originate from distant stellar processes, such as supernova explosions and stellar winds from other star systems. These particles carry information about the broader galaxy, making this region a bridge between the solar system and the Milky Way environment. Radiation levels also shift beyond the heliopause. Galactic cosmic rays, high-energy particles originating from outside the solar system, become more prominent. Inside the heliosphere, the solar wind provides partial shielding against these rays, but beyond it, exposure increases. This change affects the radiation environment experienced by any object traveling outward, making interstellar space a more energetic and variable setting. Even though the heliopause marks the edge of solar influence in terms of particle flow, gravity remains unchanged. The Sun's gravitational field continues to extend far beyond this boundary, holding distant objects in orbit even in regions where solar wind no longer reaches. This distinction between gravitational influence and particle influence becomes important in understanding the true structure of the solar system. Time and distance scales also shift in perception here. Communication delays grow longer, and signals from Earth take many hours to reach this boundary region. From a human perspective, this introduces a sense of separation, where direct interaction becomes increasingly indirect and delayed. Spacecraft operating in this region function largely independently, relying on pre-programmed systems and long-range planning. The heliosphere boundary crossing therefore represents a transition from a solar-dominated environment into a galactic one. It is not a wall or barrier, but a gradual blending of two different space conditions. One is shaped by the continuous output of a star, while the other is shaped by the accumulated material and energy of many distant stars. This interface defines the outermost reach of the Sun's immediate influence, and marks the beginning of true interstellar travel. Beyond the heliopause, space enters a region that is no longer shaped primarily by the Sun, but instead by the diffuse material that exists between stars across the Milky Way. This region is known as the local interstellar medium, a vast and extremely low-density environment composed mainly of hydrogen atoms, helium, and trace amounts of heavier elements. Unlike planetary systems or solar wind regions, this space is not organized into clear structures, but instead exists as a thin, continuous field of particles spread over enormous distances. In this medium, matter is so sparse that collisions between particles are rare events. A single hydrogen atom may travel for long periods without interacting with another particle. This creates a condition where space appears almost entirely empty, yet still contains a measurable physical presence. The density is low but not zero, and even this minimal amount of matter plays a role in shaping galactic structure over long timescales. The temperature of this region is defined not by contact heating, as in denser environments, but by the average kinetic energy of particles. Some areas are relatively warm in cosmic terms, while others are cold depending on local radiation fields and past astrophysical activity. These variations create subtle differences in pressure and density, forming irregular clouds and voids within the interstellar medium. The local interstellar medium is not uniform. It contains regions of slightly higher density known as interstellar clouds, where gas and dust accumulate under the influence of gravity and magnetic fields. These clouds are still extremely diffuse compared to planetary atmospheres, but they are significant on a galactic scale. Within them, conditions may eventually lead to the formation of new stars if compression continues over long periods of time. Between these clouds lie more rarefied regions where particle density drops even further. These void-like areas allow spacecraft to travel with minimal interaction from surrounding matter, although they are still influenced by large-scale magnetic fields that thread through the galaxy. These fields guide charged particles along curved paths, creating subtle patterns of motion, even in seemingly empty space. Radiation in this region comes from multiple sources. Some originates from distant stars, while other contributions come from energetic events, such as supernova remnants that have long since expanded into the surrounding medium. Cosmic rays, high-energy particles traveling near the speed of light pass through this space, continuously carrying energy across vast distances. Their presence makes the interstellar medium an active radiation environment despite its low density. The transition from the heliosphere into this medium is marked by a change in particle composition. Solar wind particles become less dominant, replaced by interstellar hydrogen and helium. These atoms are not bound to any single star system, but instead drift through the galaxy shaped by gravitational fields, radiation pressure and magnetic structures. This creates a slowly evolving background environment that fills the space between all stellar systems. Motion through the local interstellar medium occurs on a scale that is difficult to intuitively grasp. Distances between stars are so large that even at high spacecraft speeds, travel times extend over many thousands of years. In this region, the concept of proximity loses its everyday meaning, as nearby stars are still separated by distances far greater than anything encountered within a planetary system. The Sun itself moves through this medium as part of its orbit around the center of the Milky Way. This motion creates a directional flow of interstellar material relative to the solar system, producing a kind of interstellar wind that interacts with the heliosphere. The local interstellar medium is therefore not static, but shaped by the relative motion of stellar systems through the galaxy. Magnetic fields in this region are weak but widespread. They're not generated by a single source, but instead arise from the combined effects of many astrophysical processes across the galaxy. These fields influence charged particles, causing them to spiral and drift rather than move in straight lines. Over long distances, this results in complex pathways for particle motion, even in regions that appear empty. Dust particles are also present in the local interstellar medium, although in extremely small quantities. These grains are composed of carbon silicates and other heavy elements formed in previous generations of stars. Despite their scarcity, they play an important role in absorbing and scattering light, contributing to the faint glow and dark regions observed in interstellar space. Over time, such dust can also serve as building material for new stellar systems. Energy transfer in this region is slow and indirect. Without dense matter to carry, heat energy moves primarily through radiation and particle motion. This leads to long timescales for any significant change in temperature or structure. The interstellar medium evolves gradually, shaped by distant events rather than local interactions. The local interstellar medium also serves as a record of past cosmic activity. Its composition reflects billions of years of stellar evolution, including the remnants of exploded stars and material ejected from stellar winds. Each atom or particle in this region carries a history of processes that occurred long before the formation of the current solar system. As a spacecraft moves through this environment, it experiences near-continuous isolation from dense matter. There are no planets, no large bodies, and no significant obstacles, only a thin background of gas and dust spread across vast emptiness. Yet this emptiness is structured, shaped by the long-term dynamics of the galaxy. The local interstellar medium therefore represents a fundamental shift in scale and composition. It is no longer a region defined by a single star or planetary system, but part of a broader galactic environment where matter is distributed thinly across enormous distances. It forms the quiet space between stars, a medium that connects all stellar systems while remaining almost imperceptible in density. Within the broader structure of the Milky Way, the local interstellar medium becomes part of a much larger and more organized system, shaped by the galaxy's rotating disk. This disk is a flattened region where most of the galaxy's visible matter is concentrated, including stars, gas clouds, and dust. It forms a vast spiraling structure that slowly rotates around the galactic center over hundreds of millions of years. The environment inside this disk is not uniform, but it follows large-scale patterns that define how matter is distributed and how it moves. Stars within the disk are not fixed in place. Each star follows its own orbit around the galactic center, influenced by the combined gravitational pull of all mass in the galaxy. These orbits are not perfect circles, but slightly elongated paths that shift over time. The Sun is one such star moving through the disk at a steady pace, carrying its planetary system along with it through interstellar space. This motion contributes to the continuous interaction between the solar system and the surrounding galactic environment. The disk itself contains regions of varying density. Some areas are filled with dense molecular clouds where gas and dust accumulate into thick structures. These clouds are cold and dark, often blocking visible light from background stars. Within them, conditions can slowly lead to the formation of new stars when gravity compresses material over long periods of time. These star-forming regions are scattered throughout the disk, creating a cycle of stellar birth and evolution. Between these dense regions lie more diffuse areas filled with older stars and thinner gas. These regions are more stable and less active, but still part of the continuous galactic structure. The local interstellar medium exists within one such region, meaning that the environment around the Sun is relatively calm compared to more active star-forming zones. Even so, it remains part of a dynamic system shaped by large-scale galactic motion. The spiral structure of the Milky Way is one of the most defining features of the disk. It consists of long curved arms where stars and gas are slightly more concentrated. These arms are not rigid structures, but patterns formed by density waves that move through the disk. As material enters these regions, it becomes compressed, triggering star formation and increasing brightness. As it leaves, the density decreases again, continuing the cycle. The Sun's position within the disk is located between major spiral arms, in a region often described as a minor or interarm region. This location places the solar system in a relatively stable environment, away from the most active star-forming regions. However, over long timescales, the Sun's orbit causes it to drift in and out of spiral arm regions, exposing it to varying levels of radiation and interstellar material. Distances within the galactic disk are vast beyond ordinary scale. Even the nearest stars are separated by distances measured in light years, and travel between them would require durations far beyond human historical timeframes. Light itself takes years to cross these distances, meaning that observations of nearby stars show them as they were in the past rather than as they are at present. The disk also contains remnants of earlier stellar generations. These include old star clusters, supernova remnants, and diffuse clouds enriched with heavier elements produced by previous cycles of stellar evolution. This material becomes part of the ongoing cycle of star formation, ensuring that each new generation of stars contains more complex chemical elements than the last. Magnetic fields extend throughout the disk, though they are weak and difficult to measure directly. These fields are shaped by the motion of charged particles and by large-scale galactic rotation. They influence the behavior of cosmic rays, guiding their motion along curved paths and affecting how energy is distributed across the disk. Even though these fields are subtle, they play an important role in shaping the long-term evolution of galactic matter. The environment within the disk is also influenced by occasional energetic events. Supernova explosions from massive stars release vast amounts of energy and material into surrounding space, creating shock waves that travel through the interstellar medium. These events can compress nearby gas clouds, triggering new star formation, while also dispersing material across wide regions of the disk. Dust within the disk absorbs and scatters light, contributing to the dark lanes and glowing regions observed in spiral galaxies. This dust is composed of small solid particles formed in previous stellar environments. Although it represents only a small fraction of the total mass of the disk, it has a strong influence on the way light travels through the galaxy, shaping the visual structure of spiral arms. The motion of matter within the disk is governed by the combined gravitational influence of visible and unseen mass. Observations indicate that much of the galaxy's mass is not directly visible, suggesting the presence of dark matter, a form of matter that interacts gravitationally but not through light. This unseen component plays a major role in maintaining the structure and rotation of the galaxy, allowing the disk to remain stable over long periods. As one moves outward through the galactic disk environment, the scale of distance becomes increasingly abstract. Motion is no longer easily described in terms of everyday experience, as even the fastest known spacecraft would require vast periods of time to travel between significant structures within the galaxy. The disk is not a static background, but a continuously evolving system shaped by gravity, motion, and energy exchange. The Milky Way disk, therefore, represents a vast structured environment where stars, gas, and dust are distributed in a rotating pattern governed by gravity and long-term dynamics. It is within this environment that the solar system moves, carrying its own small region of space through a much larger galactic system. Every part of this disk contributes to the slow evolution of the galaxy as a whole, forming the setting through which any journey toward distant galaxies must eventually pass. Within the Milky Way, distance becomes a defining physical constraint that shapes every aspect of motion, communication, and energy transfer. The galaxy is not a compact object, but a vast rotating structure spanning hundreds of thousands of light years from edge to edge, with stars distributed across a thin disk and a more diffuse halo. Even regions that appear relatively close on astronomical maps are separated by intervals so large that light itself requires years or centuries to cross them. The concept of distance in this environment is tied directly to the speed of light, which represents the maximum rate at which information or energy can travel. A single light year, The distance light covers in 1 year becomes the standard unit for describing separation between stellar systems. Within the Milky Way, most stars are separated by several light years, meaning that even the nearest neighbors exist in a state of long communication delay and physical isolation. The Sun's immediate stellar neighborhood contains a small cluster of nearby stars, each moving through space with its own velocity and trajectory. These stars are not fixed in a rigid structure, but drift slowly relative to one another over time. As a result, the pattern of nearby stars changes gradually across thousands of years, altering the local stellar map, even though the large-scale structure of the galaxy remains stable. As distance increases toward the galactic center, the density of stars rises significantly. The central region of the Milky Way contains a high concentration of stellar systems, packed into a relatively small volume of space. This creates an environment where gravitational interactions are more frequent, and orbital paths are influenced by a stronger combined mass. Despite this density, individual stars still remain separated by enormous distances compared to planetary systems. In contrast, the outer regions of the galaxy contain fewer stars and more diffuse material. These regions form a halo around the central disk, containing old stellar populations and globular clusters that orbit the galactic center in extended paths. The structure of the galaxy therefore varies from dense core to sparse outer halo, with the disk acting as a transition zone between these extremes. The scale of the Milky Way becomes more apparent when considering the time required for light to travel across it. Light emitted from one side of the galaxy takes tens of thousands of years to reach the other side. This means that any observation of distant regions within the galaxy represents a view of the past with different areas showing different historical stages of galactic evolution. Spacecraft operating within the galaxy face even greater limitations. Even at the highest achievable speeds using known physics, travel between stars would require durations far beyond human lifespans. This creates a fundamental separation between the scale of human activity and the scale of galactic structure. Movement within the galaxy becomes a process measured not in years or decades, but in geological or astronomical timescales. Energy requirements for interstellar travel grow rapidly with distance. Accelerating a spacecraft to a significant fraction of the speed of light would require enormous energy input far beyond current technological capabilities. Even small increases in velocity produce large increases in required energy, due to relativistic effects where mass effectively increases as speed approaches the speed of light. Within this framework, gravity continues to play a subtle but important role. Although the galaxy is vast, its structure remains bound by gravitational forces distributed across visible matter and dark matter. This binding ensures that stars remain in orbit around the galactic center, rather than dispersing into intergalactic space. The balance between motion and gravity defines the stable rotation of the entire system. The Milky Way itself is in constant motion through space, interacting gravitationally with nearby galaxies and smaller satellite systems. These interactions can slowly distort its structure over long periods, stretching spiral arms and influencing star formation rates. However, these changes occur on timescales far longer than individual stellar lifetimes, making them gradual on a cosmic scale. Communication across galactic distances is also fundamentally limited. Signals sent across the galaxy take thousands of years to reach distant regions, making real-time interaction impossible. Any exchange of information across such scales becomes a historical record rather than an active conversation, emphasizing the separation imposed by the speed of light. Even within the galaxy, the concept of nearby loses everyday meaning. Two stars separated by 10 light-years are considered close in astronomical terms, yet this distance is still many times greater than the distance between planets in a solar system. This scaling difference highlights how planetary, stellar, and galactic structures operate in entirely different spatial regimes. The structure of the Milky Way is therefore defined not only by matter distribution, but also by the immense separation between its components. Each star system exists as an isolated island of matter within a vast ocean of space connected only through weak gravitational influence and long-range radiation. As one considers movement across the galaxy, it becomes clear that distance is not just a measure of space, but a limiting factor in all physical processes. It determines how quickly change can propagate, how systems interact, and how structure evolves over time. The galaxy is unified by gravity but separated by scale, creating a system where proximity is relative and isolation is the default condition. Galactic scale distances therefore represent a transition in understanding where familiar ideas of travel and communication no longer apply in the same way. Instead, motion becomes a slow, extended process governed by fundamental physical limits that define the structure of the universe at large. Leaving the Milky Way is not a simple extension of interstellar travel, but a transition into a different gravitational regime where the combined mass of an entire galaxy must be overcome. The galaxy is held together by the collective gravity of billions of stars, vast clouds of gas, and an extensive halo of dark matter that extends far beyond the visible disk. This creates a deep gravitational well that defines the boundary of galactic influence. The escape region of the Milky Way is not a clearly defined edge, but a gradual zone where the gravitational pull of the galaxy weakens relative to the motion of objects moving through it. Within the inner regions of the galaxy, stars are strongly bound to the galactic center, following curved orbits shaped by the distribution of mass. As distance increases toward the outer halo, these orbits become more extended and loosely bound, indicating a reduction in gravitational confinement. The concept of escape velocity applies at this scale as well, representing the speed required for an object to break free from the galaxy's gravitational influence. This velocity depends on position within the galaxy, being higher near the dense central regions and lower in the sparse outer halo. However, even in the outermost regions, the required speed remains extremely high compared to any human-made spacecraft capability. The galactic halo contains old stars and globular clusters that orbit the center in elongated, often inclined paths. These objects trace the outer structure of the galaxy, revealing the extent of its gravitational reach. Beyond this halo lies a much more diffuse environment, where the galaxy's influence gradually blends into the broader gravitational field of the local group, a system of galaxies bound together by mutual attraction. Dark matter plays a central role in maintaining the structure of the Milky Way. Although it cannot be directly observed, its presence is inferred from the motion of stars and gas, which move as if influenced by a much larger mass than visible matter alone can provide. This unseen component extends far beyond the visible disk, forming a halo that dominates the galaxy's gravitational profile and significantly increases the difficulty of escape. As one moves outward through the escape region, the density of visible matter decreases sharply. Stars become more widely separated, and interstellar gas becomes increasingly sparse. The environment transitions from structured galactic disk to a thin halo of isolated objects moving through weak gravitational gradients. This region represents the outermost layer of stable galactic membership. Even at these distances, the galaxy's gravitational influence is still present. Objects do not abruptly leave the Milky Way, but instead follow trajectories that slowly diverge from bound orbits over extremely long timescales. Some objects may remain loosely associated with the galaxy for billions of years before fully escaping into intergalactic space. The motion required to escape the galaxy depends not only on speed but also on direction. The gravitational field of the Milky Way is not uniform, and escape trajectories must account for the distribution of mass across the disk bulge and halo. A path toward the outer regions of the galaxy requires less energy than one directed toward the dense central bulge, where gravitational forces are stronger. The Sun itself is not located near the escape boundary of the galaxy, but resides in a stable orbit within the galactic disk. Its motion carries it around the galactic center over a period of hundreds of millions of years, maintaining a balance between inward gravitational pull and outward orbital motion. This orbit ensures that the solar system remains firmly within the Milky Way's structure. Objects that achieve escape from the galaxy enter a region where no single galactic system dominates their motion. Instead, their trajectories become influenced by the combined gravitational effects of nearby galaxies, intergalactic gas, and large-scale cosmic structures. This marks the transition from galactic to intergalactic dynamics. The escape region also highlights the scale difference between stellar systems and galactic systems. While planets orbit stars and stars orbit galaxies, the same physical laws govern all these motions, but the distances and energies involved increase dramatically at each level. Escape from one level requires overcoming the full gravitational binding energy of that structure. In practical terms, no known human-made object has reached velocities sufficient to escape the Milky Way. Even the fastest spacecraft travel at speeds that are negligible compared to the velocities required for intergalactic departure. This underscores the vast separation between current technological capability and galactic-scale motion. Radiation and particle environments in the escape region remain similar to those within the outer galaxy, dominated by sparse interstellar gas and cosmic rays. However, the influence of structured galactic magnetic fields becomes weaker, allowing particles to move more freely across space with fewer directional constraints. The escape region therefore represents a boundary defined not by physical walls but by gravitational balance. It is the point at which the galaxy no longer fully controls the motion of objects within it, and where external gravitational influences begin to play a more significant role. This transition is gradual and depends on both position and velocity, making it a diffuse and extended boundary, rather than a sharp edge. Beyond this region lies the wider local group where multiple galaxies interact through shared gravitational attraction. The Milky Way does not exist in isolation, but as part of this larger system, meaning that true escape from the galaxy is also a step into a broader gravitational network that connects multiple galactic systems across intergalactic space. The local group is a gravitationally bound collection of galaxies that forms the immediate cosmic neighborhood of the Milky Way. It is not a tightly packed cluster, but a loose association spread across several million light-years, where a few dominant galaxies and many smaller satellite systems interact through slow, long-range gravitational attraction. Within this structure, motion is not random but shaped by shared gravitational fields that extend across intergalactic distances. At the center of this system are two major galaxies, the Milky Way and the Andromeda Galaxy. These two spiral galaxies dominate the local group in both mass and gravitational influence. Each contains hundreds of billions of stars along with vast halos of dark matter that extend far beyond their visible disks. Their combined gravity defines the overall structure of the local group, anchoring smaller galaxies into orbit around the shared center of mass. The Andromeda Galaxy is the largest member of this pair, and is slowly moving toward the Milky Way. This motion is not rapid in everyday terms, but becomes significant over cosmic timescales. The two galaxies are bound in a mutual gravitational relationship, meaning their future evolution is tied together. Over long periods, this interaction leads to gradual changes in structure and orbital paths within the group. Surrounding these two large galaxies are numerous smaller satellite galaxies. These systems are less massive and often irregular in shape, containing fewer stars and more diffuse structures. They orbit the larger galaxies in extended paths, influenced by the combined gravitational field of the entire local group. Some of these satellites are slowly being distorted or absorbed, their material drawn into larger systems over time. The local group also contains regions of relatively empty space between its major members. These intergalactic gaps are filled with extremely thin gas and traces of dark matter, forming a faint background environment that connects all galaxies within the group. Although sparse, this material still plays a role in shaping gravitational interactions over long timescales. Distances within the local group are measured in millions of light-years, making it vastly larger than any single galaxy. Light itself requires millions of years to travel across the group, meaning that any observation of its structure reflects a deep historical snapshot of its evolution. Each galaxy is seen not as it is in the present moment, but as it existed in the distant past. The motion of galaxies within the local group is governed by their combined gravitational interactions. Unlike stars within a galaxy, which orbit a central mass, galaxies within the group move in a more complex pattern, influenced by multiple massive bodies. This creates slow evolving trajectories that change over billions of years rather than following simple orbits. Dark matter is believed to play a crucial role in holding the local group together. Its gravitational influence extends across the entire system, providing the additional mass needed to keep the galaxies bound despite their high relative velocities. Without this unseen component, the group would not remain stable over cosmic timescales. The Andromeda and Milky Way system forms a central axis of motion within the local group. Their mutual attraction creates a slow inward drift, gradually reducing the distance between them. This process unfolds over billions of years and defines the long-term future structure of the group. Smaller galaxies respond to this dynamic by adjusting their orbits, or becoming absorbed into one of the larger systems. Intergalactic space within the local group is not completely empty. It contains hot ionized gas that is spread thinly across the region, as well as traces of material stripped from galaxies during past interactions. This medium is so diffuse that it is nearly invisible, yet it forms part of the physical environment through which galaxies move. Radiation in this region includes background light from distant stars and galaxies, as well as cosmic microwave background radiation, a faint remnant from the early universe. This creates a low-level energy field that fills all of space, providing a uniform background against which all local structures exist. The structure of the local group is not static. Over long periods, gravitational interactions slowly reshape the distribution of galaxies. Some systems merge, others are disrupted, and new configurations emerge as motion continues. This evolution occurs on timescales far beyond human history, making it a gradual but continuous process. From within the Milky Way, the local group appears as a distant collection of faint galaxies scattered across the sky. Each point of light represents an entire galaxy, separated by immense distances that far exceed the scale of any single galactic system. Together they form a connected but loosely organized structure governed by shared gravity. The local group therefore represents a transitional scale in the universe. It is larger than any galaxy, but smaller than massive galaxy clusters found elsewhere in the cosmos. It demonstrates how gravity operates across intergalactic distances, binding separate systems into larger structures without requiring physical contact or dense material connections. Within this framework, the Milky Way is not an isolated system, but part of a broader gravitational environment that extends far beyond its own boundaries. The local group is the immediate context for any journey, leaving the galaxy, defining the first level of intergalactic structure that must be considered when moving toward distant systems such as the Andromeda Galaxy. Between the galaxies of the local group lies an environment that is far more empty than any region within a galaxy, yet still contains a faint and continuous presence of matter. This is the intergalactic medium, a diffuse mixture of ionized hydrogen, helium, and trace particles that drift slowly through the space-separating galaxies. It is not uniform but spread in extremely low densities, forming a vast background that fills the gravitational space of the local group. In this region, matter exists in a highly diluted state. Atoms are separated by distances so large that direct collisions are rare on timescales comparable to the age of the universe. The gas is primarily ionized, meaning electrons and nuclei are not bound together into neutral atoms but exist as separate charged particles. This condition is maintained by weak radiation fields and past energetic events that have stripped electrons from atoms over long periods. Although extremely thin, this medium is not static. It moves under the influence of gravity from the Milky Way Andromeda and smaller galaxies within the local group. This creates slow flows of gas that drift between gravitational wells, gradually reshaping the distribution of matter across intergalactic space. These motions occur over millions or billions of years, making them almost imperceptible on shorter timescales. The temperature of the intergalactic medium is generally high in cosmic terms, even though it contains very little energy per unit volume. This is because particles when present move at high speeds due to low collision rates and weak cooling mechanisms. Heat is not transferred efficiently in such a sparse environment, so energetic particles can remain hot for long periods without losing energy quickly. Within the local group, the intergalactic medium is not evenly distributed. Some regions contain slightly higher concentrations of gas, often associated with tidal streams of material pulled from galaxies during past gravitational interactions. These streams form faint bridges between galaxies containing remnants of stars' gas and dust that have been stretched across intergalactic distances. Other regions are nearly empty, forming vast void-like spaces where particle density drops even further. These areas represent the lowest density environments within the local group, where matter is so sparse that the concept of a continuous medium begins to break down into isolated particles separated by extreme distances. Dark matter also permeates this region, although it cannot be observed directly. Its presence is inferred through gravitational effects on galaxy motion and the structure of the local group as a whole. Unlike normal matter, dark matter does not interact through electromagnetic forces, meaning it does not emit, absorb, or scatter light. It forms a diffuse gravitational framework that extends across intergalactic space. The intergalactic medium plays an important role in the long-term evolution of galaxies. Over time, gas from this medium can be pulled into galaxies, providing raw material for new star formation. At the same time, energetic processes within galaxies can expel gas back into intergalactic space, creating a continuous exchange of matter between systems. Radiation in this environment is dominated by background sources. The cosmic microwave background fills all of space with a faint uniform glow, a remnant of the early universe, when matter and radiation were in a much hotter and denser state. In addition, faint ultraviolet and X-ray radiation from distant galaxies and quasars contributes to the energy background of the intergalactic medium. Travel through this region involves moving across enormous distances with almost no interaction from solid objects. There are no planets, no stars, and no dense structures to encounter. Instead, motion occurs through a near vacuum, where only occasional particles and weak radiation fields are present. Despite its emptiness, this medium defines the physical connection between galaxies. The local group's intergalactic medium is influenced strongly by the gravitational interaction between the Milky Way and Andromeda. As these galaxies move toward each other, their gravitational fields distort surrounding gas, drawing some of it inward, while pushing other portions outward. This creates large-scale flows that reflect the dynamic evolution of the group. Magnetic fields in this region are extremely weak but still present. They are stretched across intergalactic distances carried by ionized particles that drift through space. These fields influence the motion of charged particles, causing them to follow curved paths rather than straight lines. Even in such low-density conditions, electromagnetic effects remain relevant on large scales. The intergalactic medium also acts as a record of past galactic activity. Material found within it often originates from supernova explosions, galactic winds, or tidal stripping events. Over time, this material spreads out and becomes part of the broader intergalactic environment, preserving a history of energetic processes that occurred within galaxies. As the separation between galaxies increases, the role of this medium becomes more important in defining the structure of the local group. It represents the connective environment that links galaxies not through physical contact, but through shared gravitational influence and slowly exchanged material. Although extremely diffuse, the intergalactic medium is a fundamental component of cosmic structure. It fills the space between galaxies, carries remnants of their history, and participates in the slow evolution of the local group. It is through this almost invisible medium that any journey between galaxies must pass, including the vast separation between the Milky Way and Andromeda. The separation between the Milky Way and the Andromeda Galaxy defines one of the largest structured distances within the local group, yet it remains a connected system under mutual gravity. This distance spans millions of light-years, forming a vast bridge of empty space filled only with traces of intergalactic gas and dark matter. From a physical perspective, it is not a void without structure, but a low-density region where gravitational influence still operates across immense scales. Andromeda itself appears as a faint elongated spiral. When observed from within the Milky Way, its light stretched across the sky as a distant galaxy of billions of stars. Despite this appearance, it is a complete galactic system similar in structure to the Milky Way, containing spiral arms, star-forming regions, and a massive halo of dark matter extending far beyond its visible boundaries. Its motion toward the Milky Way is slow on human timescales, but significant when measured across billions of years. The space between the two galaxies is not uniform. It contains diffuse gas clouds, remnants of earlier gravitational interactions, and faint streams of material that may have been pulled from either galaxy in past encounters. These structures are extremely thin, yet they trace subtle patterns that reveal the gravitational relationship between the two systems. Over time, these streams evolve and stretch, further shaped by the combined motion of both galaxies. The concept of distance in this region is dominated by the speed of light. Any signal or particle travelling between the Milky Way and Andromeda requires millions of years to complete the journey. This means that observation of Andromeda from Earth shows the galaxy as it existed millions of years in the past, not as it exists at the present moment. The same limitation applies in reverse, creating a permanent delay in mutual observation. As motion continues, Andromeda gradually increases in apparent size within the galactic frame of reference. However, this change occurs so slowly that it is not directly observable within a human lifetime. The approach is instead measured through precise shifts in spectral lines, where light from Andromeda is slightly shifted due to its motion toward the Milky Way. This shift provides evidence of the slow but continuous inward drift between the two galaxies. Gravitational interaction between the Milky Way and Andromeda extends far beyond their visible disks. Their dark matter halos overlap in the space between them, creating a shared gravitational field that influences the motion of smaller galaxies and intergalactic gas. This overlapping region forms a dynamic gravitational environment where both galaxies shape the structure of surrounding space. Within this region, smaller satellite galaxies orbit within the combined gravitational field of the local group. Some are slowly being pulled toward one of the two dominant galaxies, while others follow extended paths that take them through intergalactic space. These motions reflect the complexity of gravitational interactions on the larger scales within the group. The intergalactic medium between the two galaxies remains extremely thin, yet it plays a role in transmitting material and energy across the gap. Over long periods, gas from this medium can be drawn into either galaxy, contributing to star formation processes. At the same time, energetic events within galaxies can expel material outward, reinforcing the exchange between systems. Despite the enormous distance, Andromeda and the Milky Way are not isolated systems. Their shared motion through the local group ensures that they are part of a single gravitational structure. This structure is slowly evolving, with both galaxies moving toward a future interaction that will occur over billions of years. The scale of this separation challenges ordinary perception of motion and distance. Even the fastest known spacecraft would require timescales far beyond human civilization to cross this gap. The journey is not limited by technology alone, but by the fundamental scale of space itself, where vast regions separate even the largest gravitational systems. Radiation across this distance is dominated by faint background sources. Light from distant galaxies, quasars, and cosmic background radiation fills the space between the Milky Way and Andromeda. This creates a uniform but extremely weak energy field that permeates all intergalactic space independent of local structures. Dark matter continues to define the gravitational framework of this region. Its distribution influences how the two galaxies move toward each other and how surrounding structures evolve. Although invisible, it provides the dominant mass component that governs the dynamics of the local group as a whole. The approach distance between the Milky Way and Andromeda therefore represents more than a simple measurement of separation. It is a dynamic region shaped by gravity, motion, and time, where two large galactic systems interact across millions of light years. This interaction unfolds slowly, yet it defines one of the most significant future events in the local universe. As this region continues to evolve, the distinction between individual galaxies and shared gravitational space becomes increasingly interconnected. The Andromeda approach distance is not a static gap, but a living structure of motion and influence, where the future configuration of the local group is gradually being determined. At the scale separating the Milky Way and the Andromeda Galaxy, the speed of light becomes the dominant constraint governing every form of observation, communication, and perceived motion. Light travels at a fixed speed in vacuum, and this constant defines how information moves across the universe. Over distances measured in millions of light years, this limit transforms space into a layered structure of delayed perception, where every signal represents a past state rather than a present condition. When light leaves Andromeda, it begins a long journey across intergalactic space, passing through regions of extremely low-density gas and dark matter. The medium it travels through is nearly empty, so the light does not scatter significantly, but the sheer distance ensures that the travel time is immense. By the time this light reaches the Milky Way, it carries information from a version of the galaxy that existed millions of years earlier. This creates a natural separation between observed reality and current reality. Within the Milky Way, the same limitation applies to all distant objects. Stars, nebulae, and galaxies are always seen as they were in the past. This effect is subtle on small scales, but becomes dominant when observing intergalactic distances. The further the source, the older the information received. In the case of Andromeda, the delay is so large that entire evolutionary stages of the galaxy occur between emission and observation. The structure of space-time ensures that no information can travel faster than light. This principle means that causal relationships are always constrained by distance and time. Events occurring in Andromeda today will not influence the Milky Way for millions of years. This separation creates distinct regions of causal independence across intergalactic space, where local events evolve without immediate external feedback. As distance increases, the delay in communication becomes a defining feature of any potential interaction. A signal sent from one galaxy to another requires a time equal to the distance divided by the speed of light. This means that even simple exchanges of information become historical records rather than real-time communication. Any response from the receiving side would take an equal amount of time to return, creating a cycle of delayed interactions spanning millions of years. The light travel limitation also affects the perception of motion between galaxies. The approach of Andromeda toward the Milky Way is not seen directly in real time, but inferred through spectral analysis. The slight shift in wavelength of emitted light reveals motion toward the observer, but this information is still delayed by the time it takes light to arrive. The actual present position of the galaxy is always beyond direct observation. In intergalactic space, the absence of matter allows light to propagate without significant absorption or scattering. This means that photons can travel vast distances with minimal loss of energy, preserving information across cosmic scales. However, this also reinforces the delay effect, as there is no medium to shorten or alter the journey time. The vacuum of space ensures that light remains the fastest possible messenger, but also the most delayed across large distances. The scale of millions of light years transforms time itself into a spatial dimension of observation. Looking deeper into space is equivalent to looking further back in time. This relationship creates a layered structure of the observable universe, where different regions represent different epochs of cosmic history. The Milky Way and Andromeda exist within the same gravitational system, yet their observable states are always separated by this temporal gap. Even within the local group, light travel time becomes significant. Smaller satellite galaxies orbiting the Milky Way or Andromeda are observed with delays of thousands or millions of years depending on their distance. This means that the local group is not seen as it is, but as it was at various points in its past, creating a composite image of different time periods. The limitation imposed by light speed also defines the boundary of the observable universe. Beyond a certain distance, light has not had enough time to reach Earth since the beginning of cosmic expansion. This creates a horizon beyond which events cannot be observed regardless of their existence. The Andromeda system lies well within this observable region, but still demonstrates the strong effects of temporal separation. In practical terms, any attempt at intergalactic travel or communication must account for this delay. Even if a spacecraft were capable of traveling at significant fractions of light speed, the communication back to its origin would remain subject to the same limitation. The separation is not only physical but also informational, enforcing a slow exchange between distant regions of space. The speed of light therefore defines more than a physical constant. It structures the way the universe is experienced from any given point. It determines how quickly change can be perceived and how far into the past observation can extend. Across the distance between the Milky Way and Andromeda, this limit becomes fully dominant, shaping all understanding of motion and position. The light travel limitation scale represents a fundamental boundary in the structure of the universe. It ensures that all large-scale cosmic interactions are delayed, all observations are historical, and all distant systems evolve independently over long periods. In the context of intergalactic distance, it transforms space into a system where time and distance are inseparably linked, defining the ultimate constraint on how the universe can be known. Within the framework of known space travel technology, chemical propulsion represents the most established method of accelerating spacecraft beyond Earth. It operates through controlled chemical reactions that release energy by breaking and forming molecular bonds, producing high-speed exhaust that pushes a vehicle forward. This mechanism is effective for escaping planetary gravity and reaching interplanetary destinations, but it has fundamental limits when considered against the scale of interstellar or intergalactic travel. The energy stored in chemical bonds is relatively small compared to the energy required to approach even a fraction of the speed of light. As a result, chemical rockets must carry large quantities of fuel to generate sufficient thrust. This leads to a structural limitation where most of a launch vehicle's mass is dedicated not to payload but to propellant. As fuel is consumed during flight, the vehicle becomes lighter, allowing acceleration to increase, but only within the constraints of the remaining fuel supply. The process of propulsion depends on the conservation of momentum. Exhaust gases are expelled at high velocity in one direction, producing an equal and opposite reaction that pushes the spacecraft forward. This principle allows motion through vacuum where no external medium is required for thrust. However, the efficiency of this process is limited by the speed at which exhaust can be expelled, which is constrained by chemical energy release. In practical terms, chemical propulsion achieves velocities sufficient for travel within the solar system, but these velocities remain extremely small compared to the speed of light. Even the fastest spacecraft produced by this method move at speeds that represent only a tiny fraction of interstellar travel requirements. This creates a vast gap between achievable motion and the speeds needed to cross even the nearest stellar distances within reasonable timeframes. As spacecraft move farther from gravitational sources, additional challenges emerge. Without atmospheric drag or planetary assistance, acceleration must come entirely from onboard energy reserves. Gravity assists where spacecraft use the motion of planets to increase speed, provide valuable efficiency gains within the solar system. But these methods rely on specific alignments and cannot be used repeatedly on interstellar scales. The outer solar system demonstrates the limitations of chemical propulsion clearly. Travel times to distant planets span years to decades, even with carefully planned trajectories. These durations arise not only from distance, but from the limited acceleration capacity of chemical systems which cannot sustain high thrust over long periods without exhausting fuel reserves. Beyond the solar system, these limitations become absolute. The energy required to reach even the nearest stars using chemical propulsion exceeds practical limits by many orders of magnitude. The exponential relationship between velocity and energy in relativistic conditions means that small increases in speed require disproportionately large increases in energy input. Chemical reactions simply do not provide the necessary energy density to bridge this gap. The structure of chemical fuels also imposes physical constraints. Fuel must be stored in tanks carried during acceleration and managed throughout the mission. This introduces additional mass that further reduces efficiency. As missions extend in duration and distance, the proportion of fuel to payload becomes increasingly unfavorable, limiting the feasible range of travel. In comparison to interstellar distances, the capabilities of chemical propulsion remain confined to a narrow region of space. It is effective for reaching planets, moons, and some distant objects within a solar system, but it does not scale to the distances separating stars, let alone galaxies. The Milky Way and Andromeda are separated by millions of light-years, a scale that renders chemical propulsion functionally negligible. Even hypothetical extensions of chemical systems would not resolve this limitation. Increasing fuel capacity or improving combustion efficiency provides only incremental gains. The fundamental barrier lies in the energy density of chemical bonds, which is fixed by molecular structure. To achieve interstellar or intergalactic travel, entirely different physical mechanisms would be required far beyond the scope of chemical reactions. Another limitation arises from time. Chemical propulsion systems must operate continuously, or in stages over long periods to achieve maximum velocity. However, extended operation introduces mechanical wear system degradation and resource depletion. These factors further reduce the practicality of a long-duration acceleration required for deep space travel. Within the context of galactic-scale distances, chemical propulsion effectively defines a lower boundary of mobility. It allows movement within planetary systems, but does not provide a pathway beyond them. The transition from solar system travel to interstellar travel marks a shift from chemical energy to hypothetical high-energy physics, where entirely different propulsion concepts would be necessary. Despite its limitations, chemical propulsion remains foundational for space exploration. It enables access to orbital space planetary surfaces and outer solar system regions, forming the basis for all current space infrastructure. However, when placed against the scale of the Milky Way and the distance to Andromeda, its limitations become absolute and defining. The chemical propulsion limit therefore represents a technological boundary shaped by the fundamental properties of matter and energy. It defines the practical reach of current civilization within space, and highlights the vast separation between known engineering capabilities and the requirements of intergalactic travel. Within this framework, the journey to even the nearest galaxy remains far beyond the reach of chemical energy systems. As motion approaches a significant fraction of the speed of light, the structure of space and time begins to change in ways that alter every aspect of travel. This regime is described by relativistic physics, where classical intuition about velocity, mass, and energy no longer applies in a linear manner. Instead, time, distance, and energy become interdependent, creating constraints that fundamentally limit high-speed travel across interstellar and intergalactic distances. One of the primary effects in this regime is the increase in energy required to continue accelerating an object as its speed rises. As velocity increases, additional energy produces smaller and smaller gains in speed. Near the speed of light, the energy required to approach further increases becomes extremely large, effectively preventing any object with mass from reaching or exceeding this cosmic limit. This creates a natural boundary in achievable velocity. Time itself also behaves differently under relativistic conditions. For an object moving at high speed, time passes more slowly relative to a stationary observer. This effect, known as time dilation, becomes more pronounced as speed increases. While this might suggest a potential advantage for long-distance travel, it does not reduce the energy requirements needed to reach such speeds, nor does it eliminate the constraints imposed by acceleration and deceleration. Length contraction is another consequence of relativistic motion. From the perspective of a fast-moving object, distances in the direction of travel appear shorter. In principle, this could reduce the perceived distance between galaxies such as the Milky Way and Andromeda. However, this contraction applies only within the moving frame, and does not change the distance measured by stationary observers. The underlying separation between galaxies remains unchanged in the external reference frame. The combination of these effects creates a complex structure of motion, where travel time, perceived distance, and energy requirements do not align in simple ways. Even though relativistic effects alter perception, they do not remove the fundamental energy barrier required for acceleration. The closer a spacecraft moves toward light speed, the more extreme these constraints become. Radiation exposure becomes another critical limitation in relativistic travel. At high velocities, even sparse interstellar particles become highly energetic impacts due to relative motion. A single hydrogen atom in the interstellar medium can carry significant kinetic energy when encountered at relativistic speeds, turning otherwise harmless space into a hazardous environment filled with high-energy collisions. Shielding against this radiation requires additional mass, which in turn increases the energy required for acceleration. This creates a feedback loop where protective measures further reduce efficiency. The balance between safety and performance becomes increasingly difficult to maintain as speed increases. Relativistic travel also imposes constraints on communication. Signals sent between a fast-moving spacecraft and a stationary observer experience frequency shifts and time delays that increase with velocity. This makes real-time communication progressively more distorted and delayed, eventually reducing interaction to highly time-stretched exchanges of information. Even if a spacecraft were capable of maintaining near-light speed for extended periods, the processes of acceleration and deceleration remain limiting factors. Achieving such speeds requires enormous energy input, while slowing down at the destination requires an equivalent amount of energy. Without a mechanism to bypass these requirements, the total energy cost of interstellar or intergalactic travel remains extremely high. In the context of the Milky Way and Andromeda, relativistic constraints define the theoretical lower limit of travel time between galaxies. Even at speeds approaching light speed, the distance between these galaxies ensures that journeys would still span millions of years in external reference frames. Time dilation may reduce the experience duration for travelers, but it does not eliminate the physical separation or energy cost involved. Another important factor is the stability of matter at high velocities. At relativistic speeds, interactions with even low-density interstellar gas can produce intense particle showers and secondary radiation. These effects increase with velocity, making sustained travel through interstellar or intergalactic space increasingly difficult to manage without advanced protective systems. The structure of space-time itself remains consistent under these conditions, meaning that no known physical process allows for shortcuts through space without violating established causal relationships. The speed of light remains the universal limit for information and energy transfer, ensuring that all relativistic motion remains bound within the same fundamental constraints. Relativistic travel therefore represents a boundary not of engineering alone, but of physical law. It defines the ultimate framework within which all motion through space must occur. While it allows for extreme velocities and significant time distortion effects, it does not provide a means to bypass the vast distances separating galaxies. Within this framework, the journey between the Milky Way and Andromeda remains governed by the same underlying limitations that apply throughout the universe. Even at relativistic speeds, the scale of intergalactic distance ensures that travel remains an endeavor measured in cosmic timescales, reinforcing the separation imposed by the structure of spacetime itself. When all known layers of cosmic distance, propulsion limits, and relativistic constraints are combined, the journey from the Milky Way to the Andromeda Galaxy resolves into a single defining factor: time. The separation between the two galaxies is so vast that even the most extreme physical scenarios still result in durations that exceed ordinary biological, civilizational, and geological scales. The structure of the universe sets the framework, but time determines the outcome. The Andromeda Galaxy lies at a distance of roughly 2.5 million light-years from the Milky Way. This means that light itself requires 2.5 million years to cross the gap. Any object travelling more slowly than light must therefore take longer, regardless of propulsion method or trajectory. This establishes a baseline duration that cannot be reduced by conventional physics. At velocities achievable by current spacecraft, the journey becomes effectively impossible within meaningful timeframes. Even with continuous acceleration far beyond present engineering capability, travel times extend far beyond the duration of recorded human history. The scale of distance ensures that no incremental improvement in propulsion meaningfully changes the overall outcome. Even under idealized relativistic conditions where a spacecraft approaches a significant fraction of the speed of light, the external observer still measures travel times in millions of years. Time dilation may reduce the experience duration for those on board, but it does not alter the fact that the journey unfolds across vast cosmic intervals in the external universe. The galaxy itself continues to evolve during this time, with stars forming, aging and dying long before arrival. The gravitational structure of the local group also evolves during such a journey. The Milky Way and Andromeda continue moving toward each other, gradually altering the geometry of the space between them. Over hundreds of millions of years, their mutual attraction leads to a slow convergence, meaning that any long-duration trajectory exists within a changing gravitational landscape rather than a fixed path. Energy constraints reinforce these temporal limits. The amount of energy required to accelerate a spacecraft to near light speed and then decelerate it at the destination grows beyond practical bounds. This requirement is not a technological limitation, but a direct consequence of relativistic energy relations, where mass-energy equivalence defines the cost of motion at extreme velocities. The intergalactic medium between the two galaxies adds only a minimal physical obstacle, yet its presence becomes significant at high speeds. Even sparse particles can generate extreme radiation effects when encountered at relativistic velocities, further complicating sustained travel. This environment remains thin but persistent across the entire journey. From a human perspective, the scale of 2.5 million light-years removes the concept of travel as a continuous experience. Instead, it becomes a transformation across epochs. Civilizations capable of initiating such a journey would not experience it as a single act, but as a sequence of generation systems or even entirely different forms of existence evolving independently over time. The Milky Way and Andromeda themselves are not static destinations. They are dynamic systems undergoing constant internal change. Spiral arms shift, star clusters disperse, and new stars form while others collapse into remnants. Over the duration of an intergalactic journey, the target galaxy would evolve into a different configuration long before arrival. The eventual interaction between the two galaxies adds another layer of complexity. Their mutual gravitational attraction ensures that they are not merely separated, but on a slow collision course over billions of years. This means that the concept of travelling to Andromeda becomes entangled with the concept of both galaxies merging into a single larger structure in the distant future. Within this context, the idea of human-scale duration becomes almost irrelevant. Biological lifespans, even when extended through hypothetical future technology, remain negligible compared to the timescales involved. The journey exists entirely outside ordinary temporal experience, defined instead by the long evolution of cosmic structures. The final implication is that intergalactic travel, when measured against known physical laws, does not fail because of a single barrier, but because of the combined effect of distance, energy, time, and causality. Each factor reinforces the others, creating a layered constraint system that defines the limits of motion in the universe. The journey to Andromeda therefore represents not a practical voyage, but a conceptual boundary in physics. It illustrates the relationship between scale and possibility, where the size of the universe directly determines what can and cannot occur within it. Even when all known mechanisms are considered, the result remains consistent. The distance is real, the time is immense, and the passage is governed entirely by the fundamental structure of space-time.